So here we are going to start with a table of some frequently used Taylor series. So these are actually all going to be familiar. We've talked about these in one shape or form previously, but here they are listed all together for you. So this might be a nice resource to use. And I'm going to do a couple examples here. We're going to use this table to find the sum of some series. So the first one is pi over 3 minus pi cubed over 3 cubed times 3 factorial plus pi to the 5th over 3 to the 5th times 5 factorial minus pi to the 7th over 3 to the 7th times 7 factorial. And if you look at that table 10.1, this hopefully will look familiar, at least familiar enough to here with the sine function. So this is actually the sine function where x is going to be pi over 3. So this is equal to sine of pi over 3. And we can actually figure that out. Sine of pi over 3 is just the square root of 3 over 2. The second one is x cubed plus x to the 4th plus x to the 5th plus x to the 6th, and so on. And I'm going to rewrite this as x cubed times 1 plus x squared plus x cubed, and so on. So now I'm going to look for this in that table, 1 plus x squared plus x cubed, and so on. Well, it's at the very top here. 1 plus x squared plus so on is equal to 1 over 1 minus x. So I have x cubed times 1 over 1 minus x, which is just x cubed over 1 minus x. Makes things very easy to work with. Then the very last page of notes here, I've got this definition, and it says, for any real number theta, e to the I theta equals cosine theta plus I sine theta. In case you're wondering, where did this come from? If you substitute x equals I theta into the Taylor series for e to the x, you're going to get this. And this is called Euler's identity, and it lets us define e to the a plus bi to be e to the a times e to the bi power for any complex number. And so it says e to the a plus ib is equal to e to the a times cosine b plus I sine b. So I've got a note here that says a consequence of this identity is the equation e to the I times pi power. That equals -1. And if you move that -1 to the left, you've got e to the I times pi plus 1 equals 0. It says this is 5 of the most important constants in mathematics in one relatively simple equation. Kind of interesting. So to wrap things up here, we're going to do a bit of a proof more than anything else. It says use the definition of e to the I theta to show that for any real numbers theta, theta sub 1, and theta sub 2, e raised to the I theta sub 1 times e raised to I theta sub 2 equals e to the I times theta sub 1 plus theta sub 2 powers. And you might be thinking, well, just plain old properties of exponents can help us here, but we're going to use this definition and some trig identities to help us. So I'm going to start with e raised to the I times theta sub 1 times e raised to I theta sub 2. By definition, e raised to I theta sub 1 is equal to cosine and I'm just going to call it theta 1 if you don't mind, plus I sine theta 1. E raised to the I theta 2 is going to be cosine theta 2 plus I sine theta 2. And let me scroll down now. So now I'm just going to multiply. I'll use FOIL. So that's cosine theta 1 times cosine theta 2. Then with the outside, we're going to have plus I cosine theta 1 sine theta 2. Then on the inside, we'll have I sine theta 1 cosine theta 2. Then finally, we'll have plus I squared sine theta 1 sine theta 2. If you remember, I squared is equal to -1. So this last term, instead of plus I squared, it's just -1. Or simply minus. So now what I'm going to do is I'm going to separate this. I'm going to pull out the real parts and separate off the imaginary parts. So I'm going to have cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. I just realized that I wrote sine theta 2 twice. Fix that. Plus I times. Now I'm going to actually flip the order of these two. I'm going to put this term first and this other term second, just to make it match the trig identity a little better. So what we have here, cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, that's actually cosine of theta 1 plus theta 2. And again, that's just a trig identity. And sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2 is another trig identity. This is equal to sine theta 1 plus theta 2. And so what we've done here is, instead, if we go back up to Euler's identity, instead of just having a theta, we have the theta 1 plus theta 2. So we can say that this is equal to e raised to the I times theta 1 plus theta 2 power.